All right, so here we are. You guys have looked at some of these definitions. I've asked you to go through your textbook and to jot down the meanings of these words. So we're going to see how well you did as we go through the lessons. We're going to talk about each of these. And so you can refer back to those notes and make sure you got everything right. So you should have a set of blank notes in front of you. We're going to start on chapter 11 here today and going to get you to fill in some of those blanks as we move through. All right, so chapter 11, we're going to talk about scientific theories and other theories too about the origin of the universe. We've already talked about this, but theories about different things to do with space. So galaxies in the universe, and I'll try and highlight what you should be filling in with your blanks there, just so we're all clear. Galaxies in the universe. Okay, now remember, we are in the Milky Way galaxy, but there are thought to be maybe billions of galaxies in the universe. The universe is so huge. And so galaxies that we've been able to observe, and I'll explain how we know this later, but they are thought to be moving away from one another. Okay, so they're thought to be moving away from one another. So galaxies are moving. Everything's moving in the universe, and some things are moving one way, some things moving the other way. We have found that galaxies are definitely moving away from one another. Things are spreading out a little bit. When light is emitted from an object that is moving away from us in space, the spectral lines, okay, so that's one of the things that I asked you to look at. The spectral lines, what are they? They are basically wavelengths of light that show up on the electromagnetic spectrum. And I don't have a diagram here, but I will show you a diagram later that shows spectral lines. But these are specific wavelengths of light. So I don't know if you guys knew this, but the different colors that we see, the reason why we see different colors is because there are different wavelengths of light that are coming into our eyes, and that we are interpreting these different frequencies and different wavelengths of light. So different colors have different characteristics. And some colors are absorbed and some are reflected away, and so that's why we see different colors. And anyways, spectral lines, there's a lot. If you continue, well, when you continue on, and if you take Physical Science 20, we're going to talk a little bit more about spectral lines, and Chemistry 30, we'll talk about spectral lines. And I imagine in Physics 30, I haven't taught that for a while, but you'll talk about these spectral lines, electromagnetic radiation. But these specific wavelengths of light seem to shift further to the red end of the spectrum, Okay, when light is emitted from an object moving away from us in space, the spectral lines, and we would have an expectation of where these lines would show up, what frequencies, what wavelengths, but we notice that they're all shifted just a little bit towards the red end of the spectrum. Light from distant bright objects in the universe exhibit this red shift. It's called red shift. Okay? So scientists believe that the universe then is expanding. And due mostly to this observation of the light that's coming from distant stars and galaxies, that there is this kind of red shift. Okay? So why does redshift happen? Let me just show you these two diagrams, and you have these on your notes paper as well. So something called the Doppler Effect. Now, we notice the Doppler Effect with sound mainly. So think about this. If you hear an ambulance, I think we have a picture of an ambulance here in this little diagram. If an ambulance is stopped at a stoplight or on the side of the road, and you hear the siren, okay? It's kind of like, wee, wee, wee. That's actually, I don't know what, that's not really a siren. Wee, 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 right? Okay, so no, you like the first one better? I feel like I'm in like London or something. Yeah, that's like UK or something. Anyways, but when it's stationary, it has a predictable kind of consistent sound, right? It doesn't change much. It's just like either loud or soft, depending if you're close or far away. The wavelength of the sound, so the waves are emanating out from the ambulance siren evenly. But when the ambulance is moving, we hear something different. And again, we'll study more of this in Physical Science 20, but you've all heard this with sirens or with horns or with any other noise coming from a moving object. So for example, a siren, when the ambulance is moving, would sound something like this. It would be like, and it kind of, the pitch changes, the actual sound. You like that? I'll do that again. So when it's coming towards you, the pitch, it gets kind of higher, and then when it drives away from you, when it passes you and drives away, the pitch gets lower. So coming towards you kind of goes like this, and then when it passes you and goes away, it sounds like, I don't know if you guys have ever noticed that.
Yeah.
You ever noticed that? Okay, what about a horn, okay? If the car is sitting and you lay on the horn, this is like, okay? That's a stationary object. Yeah, I'm in fine form here today, making all these sounds. But when a car is driving towards you and passes you, okay, why don't you guys show me now? Why don't you guys do it? Show me, what does the horn sound like when a car is approaching you and then it passes you driving on the road? Ready? Go. Okay, that was interesting. Okay, wait, no, just wait. What I heard was this. No. I just heard the horn getting louder and then the horn getting quieter. But that's not what happens. The horn actually goes like this. It goes.
That's exactly what we
That wasn't that
did.
perfect?
You did the exact same example as you did.
No, I didn't do the exact same.
Oh, it sounded the same.
Before, you guys just got louder, like. That's different than. Even the car driving by, it's like. It's like. Am I getting through to you here? Is this some yes, some no? Okay. You just like watching me make these silly noises. Okay, but listen. This is why this happens. Look. When the vehicle is driving towards you, you're in the front here, okay? So you're over here. This is you right here. And look at these wavelengths. You see the wavelengths? How they're piling up. And so you hear a sound that's a high frequency or a high pitch. When the vehicle has passed you and you're over here, what you hear is a lower frequency or a lower pitch sound, because the vehicle is traveling one way and the sound waves are going the other way, so they're kind of like spreading out a little bit. So they pile up. Now think about this. A duck swimming in a pond. It's very still, and then you've got a duck or you've got a goose or something swimming in the pond. What happens? This is exactly what it looks like. You have the waves are, they pile up in the front and they're big and spread out in the back. That's exactly what's happening with sound. Now, that's also exactly what's happening with the light. Okay, so let's move over here. And this diagram here is showing, so this would be a spectral line. Let me see if I can highlight this. A spectral line right here, okay? That is a specific frequency. We've got a spectral line. And when an object, let's say a galaxy, is not really moving away or coming towards the Earth, we would expect spectral lines of light to be in a certain position. If the galaxy is, or the distant light source is traveling away from us, then the wavelengths are spread out and these spectral lines move a little bit towards the red end of the spectrum over here. If a galaxy or a distant object is moving towards us, we would interpret the same bit of light with frequencies that are shifted the other way, so towards the blue end of the spectrum, okay? So that's how scientists can determine, or at least this is our best determination as to what's happening with the motion of galaxies and distant planets. Expansion of the universe is support for the secular view of the Big Bang Theory. We talked about that. So initial explosion, if we had an explosion, things should be kind of traveling away from the center of the explosion, let's say. Matter would seem to be moving from a central point. This expansion that we witness is also supported by a biblical theological perspective, according to Isaiah 40:22. And we've talked about some of these ancient biblical verses too that talk about the creation of the world and things like this. I don't know if you knew that this one was in there. Isaiah 42 says this: It is he who sits above the circle of the earth. Interesting. People back in the day thought the earth was flat, but I don't know. The Bible said it was a circle a long time ago. And its inhabitants are like grasshoppers, really small. It is he who, this is really cool, stretches out the heavens like a curtain and spreads them like a tent to live in. So it seems to indicate that Isaiah is seeming to indicate to us that God is stretching the heavens. And if the heavens or the universe is expanding, that sure would sound like a bit of a stretch to me. Now, the stretching or the expanding of the universe provides for gravity and different things like that to actually be a thing, which I think I mentioned yesterday. But anyways, the universe is expanding, and that is what the best guess that we have from what we can observe. Let's talk about planetary motion, okay? So the motion of planets. The geocentric model of planetary motion, and let's see, we want to highlight geocentric there. The geocentric model. Now, this word geocentric, you would have defined this from your textbook earlier yesterday. Geo is the first part. Geo means earth. Centric is center. So earth-centered model. This was believed for more than 2,000 years, and it stated that the earth was the center of the universe. The earth was the center of the universe. And that the sun and moon and planets revolved around it. Okay? So the early view of what we saw, and I mean, I guess if we're just standing here on the earth, looking around up at the night sky, and all of a sudden the sun comes up, I put that in air quotes, the sun comes up in the east and it travels across the sky and goes down in the west. From our perspective, it probably would look like the sun is going around the earth, right? And then the moon, wow, the moon comes up and the moon goes down. Oh, okay, so the moon's revolving around the earth. Well, we got that one right. But we are actually spinning and traveling around the sun. Okay, so that wasn't determined until later. So about 600 years ago, okay, not too long ago really, scientists including Copernicus, and I think I got you to fill in 600 years, Copernicus, Galileo. Interesting thing about Galileo, when you're listing scientists, you always refer to scientists by their last name, except for Galileo. Did you know that Galileo was his first name? His name was Galileo Galilei. Galileo Galilei. And they always refer to him as his first name, Galileo.
Because Galileo is hard to say.
I don't know. It's a good. There's probably some reason. I don't know. This is kind of a cool observation. And also Kepler and Newton. So Sir Isaac Newton. And he was responsible, among some others, but mostly him, were responsible for calculus, which is like my favorite. Revised this theory to make the sun the center of our solar system. So not really speaking of the entire universe, but at least the sun is the center of the solar system, so the earth would revolve around the sun instead of the opposite way around. This is referred to as the heliocentric model, helio. And I noted down below here, just a reminder, geo means earth, helio means sun. So earth-centered and sun-centered, okay? So this is chapter 11. These are some of the important things that I wanted to highlight for you. You should read through chapter 11. There are lots of diagrams and lots of things in your textbook that would be of interest, and they would fill in the information that we brought forward here too. There are many other things that we could study, but these are the highlights for chapter 11. All right, retrograde motion. That was another thing that I asked you to look into in your textbook there. What is retrograde motion? Well, if you take a look at the word, and here's a hint. When you're looking at scientific words, if you examine the word closely, you'll be able to most times figure out what the meaning of the word is, even though it's brand new to you. So for example, even the previous slide, okay? Geocentric. Did you notice that I split that up into geo and center? Earth. Geo means earth. Geology. Ology is the study of. Geo, earth. So geology is the study of the earth. Biology. Ology is the study of. Bio is living things. So we can take words in science, and we can examine them closely, and usually there's some kind of piece, if not two pieces of a word, that you will be able to help you understand what's going on. Did you notice this word retro in the term retrograde? Okay, so what does retro mean? It means like old style, right? Like back in time almost. Like, oh, that's retro. There's going to be retro payments. Okay, so they're going to go back in time and pay you for stuff that happened a long time ago. Or that outfit is really retro, Mr. Maxwell. I get that all the time. It's like, yeah, it's from like 1980s. Okay, retro, right? Or retrofit means to go back and redo something that's old. So it's kind of like going back. So retro means going back, and retro motion or retrograded motion would be motion that appears to go forward and back. Retro. So the differences in orbits of planets, let's talk about this. Make motion of planets seem to move forward, then move back in the sky. So you guys don't have any blanks in your copy right now, do you? Okay. So the differences in orbits, motions seem to move forward and then move back in the sky. For example, Earth is catching up to Mars in its orbit, then it's passing it, then it's moving ahead. Okay? Now, if we take a look at these two diagrams, it's a little bit tricky to understand, but I like these two diagrams. I think they really help us. So here's the sun, here's the Earth, it's revolving around the sun. Here's Mars out here, okay, the next planet away, and it's moving too. It's moving maybe a little bit slower. Okay, do you see how the Earth seems to be passing here pretty quick, and then Mars is going a little bit slower? You see that? Now, when we look at Mars from this position right here, let's say, Mars appears to be right here. As Earth moves, it's moving a little bit quicker than Mars. We look at Mars and we see it to be right about here. Okay, I don't know if you can actually see that, but so here's the first position. Here's the second position. Now, here's the third position over here. Here's the fourth position. But when Earth kind of catches up to Mars in a sense, look what happens. The path of Mars here is going left in the sky. It's moving across the sky. But now it's going back towards the right. So it's moving this way, but then it kind of curls back around because of these sight lines, okay? When Earth passes Mars, it appears to kind of go backwards in the sky, and then you get to a point where it starts moving again, and then it starts following along. So this is what it looks like over here if you were to actually sort of map, over a long period of time, what is happening to Mars. It appears to be moving, left, let's say, in the sky. And then all of a sudden, wait a minute, it's going right. What's happening here? Mars is on a little bit of a joyride. And this is what happens. Well, this is because of the relative positions of Earth and Mars in the orbit. Okay, so that's what retrograde motion is. It appears that planets that we view from Earth appear to be moving forward and then retro going back in motion, which isn't true, but we can see that it's because of the different relative positions and orbits that we might see it like that, okay? Now, the constellations, right? This kind of thing doesn't happen with the constellations because the constellations are so far away, they might be moving a little bit, but they're not moving enough for us to notice any difference over a short amount of time. And two, they're far away, and two, they're not revolving around the sun like we are, and so it's the perspective, okay? Any questions about that?